The modern wellness space is saturated with tutorials on the dopamine detox. The popular pitch suggests that by locking away your devices and sitting in silence, you can deplete your dopamine levels and refresh your brain. Physiologically, this is impossible. You cannot fast from a naturally occurring neurotransmitter that your body requires for basic survival and movement. The original clinical formulation, developed by psychiatrist Dr. Cameron Sapa, is actually a highly specific form of cognitive behavioral therapy. It targets 6 specific categories of compulsive, distress-inducing behaviors, like excessive gaming and emotional eating, or chronic scrolling. The actual protocol focuses on managing these triggers, rather than enforcing total asceticism. To understand what this therapy actually treats, we have to look at the brain's reward system. This is the mesolimbic pathway. Dopamine is produced in the ventral tegmental area and travels to the nucleus accumbens, while maintaining a critical feedback loop with the prefrontal cortex. Dopamine traveling this specific route regulates motivation and learning. It acts as the chemical drive that pushes you toward a goal. The clinical objective of dopamine fasting centers on reversing postsynaptic receptor downregulation, a physical adaptation your brain makes when it is overstimulated. This process focuses on restoring the prefrontal cortex's executive control over the limbic system's impulsive loops. A foundational error in popular wellness culture is equating dopamine directly with the physical sensation of pleasure. This illustrates the actual neurobiology of reward. On the left, endorphins and endogenous opioids bind to receptors to create consummatory pleasure, the sensory liking. On the right, dopamine binds to D1 receptors to create incentive salience, the wanting. Endorphins mediate sensory enjoyment, while dopamine provides the intense, goal-directed motivation to obtain it. This chart maps out a mathematical algorithm known as reward prediction error, or RPE. Notice that when a cue, like a phone notification, appears, there is a massive spike in dopaminergic firing before the reward is actually consumed. Dopamine neurons signal the discrepancy between expected and actual outcomes. Through temporal difference learning, this neurochemical burst eventually shifts away from the reward, mapping directly onto the earliest predictive cue. Digital cues like pings, vibrations, and unread badges consistently hijack this exact mechanism. This predictive firing locks the brain into a continuous seeking loop. It drives you to instantly pick up the phone, even if the activity itself has completely stopped delivering satisfaction. When this seeking loop is hyperstimulated by infinite digital abundance, the brain activates its defense mechanisms to maintain equilibrium. Look closely at a synaptic cleft flooded with dopamine. These red structures are presynaptic D2SH autoreceptors, which monitor dopamine concentration in the gap. When they detect excess dopamine, they trigger a negative feedback loop to suppress synthesis and limit vesicle release. Simultaneously, the postsynaptic D2 receptors physically recede, reducing in density to protect the neuron from overstimulation. Dr. Anna Lemke conceptualizes this receptor downregulation as a teeter-totter. When a high-stimulus reward tips the balance toward pleasure, neuroadaptation gremlins jump onto the pain side to force it back to level. The problem is the brain's homeostatic response overcorrects. The gremlins stay on the balance, driving it below your normal baseline. This creates the dopamine deficit state, a neurological condition characterized by chronic anhedonia, anxiety, and high impulsivity. Because your receptor density is severely compromised, normal low-intensity rewards, like reading a book or having a face-to-face conversation, fail to register. Digital consumption now serves a purely functional role, elevating the dopamine baseline just to reach a state of normalcy and alleviate the distress of withdrawal. To understand why we lose control of these habits, we have to look past the limbic system and examine the prefrontal cortex, the brain's executive control center. This schematic illustrates the prefrontal cortex acting as a top-down brake, projecting a strong inhibitory signal to the nucleus accumbens to suppress impulsive firing. But the prefrontal cortex operates with a strict structural limitation known as the psychological refractory period, creating a hard processing bottleneck. Think of this executive center as a single-lane bridge, configuring one task rule set at a time. When constant digital notifications flood in, they jam this bridge. Every time you switch contexts, your brain must deactivate one rule set and activate another. This drains cognitive resources and leaves residual interference in your working memory. Constant digital switching inevitably leads to severe prefrontal exhaustion. When that cognitive overload peaks, the inhibitory signal from the prefrontal cortex flickers and fails. The nucleus accumbens is now firing unchecked. Without the prefrontal brake, hypersensitized limbic loops take total control, and casual habits mechanically transform into compulsive behaviors. This brings us to the actual clinical utility of the dopamine fast. It serves as a structural intervention to rebuild the compromised synapse. Strict time boxing of digital stimuli forces the nervous system to adapt to the absence of artificial spikes, which mechanically upregulates D2 receptors over time. You can accelerate this repair process through hormesis, using controlled physiological stressors like cold or heat to naturally rebalance the system. Intentionally engaging the pain axis triggers a gradual, sustained dopamine release. Because this dopamine is synthesized as a homeostatic corrective response rather than an artificial spike, it stabilizes the system without plunging the brain into a subsequent deficit state. This animation shows neuroplasticity occurring during controlled stress. The mTOR pathway activates, phosphorylating the ribosomal protein S6, which leads to the physical insertion of new GLU-A1 receptors into the postsynaptic density. This structurally remodels the synapse, increasing its sensitivity to natural dopamine levels. Clinical mindfulness practices further support this by actively thickening the functional connectivity tracts between the prefrontal cortex and the reward circuits. This structural repair restores the sensitivity required to perceive natural, everyday pleasure. Setting realistic expectations for this recovery requires looking at clinical data for dopamine receptor repair. This chart tracks D2 receptor availability over a 24-month period based on data from severe methamphetamine addiction, highlighting the brain's capacity for neuroplastic repair. While acute withdrawal causes immediate anhedonia, measurable receptor upregulation begins within weeks of targeted stimulus restriction. Dopamine fasting functions as a targeted behavioral restriction rather than a permanent rejection of pleasure or a literal neurochemical cleanse. The true goal is repairing the top-down executive control of the prefrontal cortex so it can properly manage the limbic system. Reclaiming this executive control allows individuals to disengage from compulsive loops and restore behavioral flexibility.